Hi guys, so today we would be studying a very important property, that is Archimedean property. It's very important. So before that we have to actually study about order completeness property, and it is also called as least upper bound property. So let us just understand what it is. So its statement is every non-empty subset of R which is bounded above has the supremum in R. So there is this non-empty subset of R, let us say S, a subset of R, okay, which is bounded above, which means set S has upper bound. Again, I will explain what upper bound is. If you want to get into the detail of what upper bound is, you have to check my previous videos. So upper bound is nothing but there exists an element in R, and the element R is greater than all the elements of set S. Then the element which is in R is said to be the upper bound of set S, and that set S is called to be bounded above by the element which is in R. Which is bounded above, which means S has upper bound, has the supremum in R. Now it says that if S is bounded above, then it will have a supremum. Now again I have explained what supremum is. Supremum is nothing but the least upper bound, which means the smallest element of all the other upper bounds is called as supremum. So if there exists a upper bound of S, then there exists a least upper bound of S. That's what order completeness property is, okay? The statement of Archimedean property is for every positive real number x, there is a natural number n naught such that x is less than n naught. So every positive real number x. Now every positive, which means any real number which is only positive. Okay, that's the number which they are going to consider as x. There is a natural number n naught. Okay, so we know what is natural number. Natural number begins from 1. So 1, 2, 3 and so on. All of that is natural number. So any natural number they have chosen to be n naught. And there is this condition which they have given such that x is less than n naught. We will see the proof of this now. Okay, so the proof is let x belong to positive real number. Now according to our Archimedean statement, we can see that for every positive real number x. Now real number is nothing but R, and positive is represented like this, okay, positive sign above the real number. Then there is natural number. Natural number is represented like this, we all know that. And then there's this condition which is x is less than n naught. We're going to use all of this information in our proof, okay. So first of all, we say that let x belong to real number. Then we say that, okay, so we have supposed that there is no natural number n such that x is less than n. So we say that this condition right here does not exist, okay. This condition here does not exist. So what we do now is we reverse the condition and we put it up like this. So let n be less than equal to x, and we know that n belongs to natural number. Then we write therefore n is bounded above by x. Why is n bounded above by x, you would be thinking. Have you clearly seen what I've written? N is nothing but it is a set, okay. This small n belongs to this set n, right? And all the elements or just single element of this n is small than this x, okay, which means this element is greater than all the elements which belong to this set n, which means clearly that x here is the upper bound of set n, right? Because it is greater than all the elements of set natural number. That's why n is bounded above, or x is the upper bound of n. That is nothing but n is bounded above by x. Now they've written since this natural number set is subset of R. We have seen that. Why I'm saying that? We have seen that previously in this diagram right here. Natural number comes inside whole number. Whole number comes inside integer. Integer comes inside rational number. Rational number comes inside real number, which means natural number is nothing but subset of real number, right? So that's what they have said. Since natural number set is subset of real number, by order completeness property, supremum n exists in R. We have seen what order completeness property means, right? Every non-empty subset of R, which we have taken n here, okay? Every non-empty subset of R, that's what we are talking about, n, which is bounded above. Is it bounded above? We have proved that. It is bounded above. We get that. Has supremum in R. So if it is bounded above, and therefore it has supremum in R. Okay, so supremum of n exists in R, which means least upper bound of set n exists in R. That's what they are trying to tell us. Then we write, so the supremum of n exists, we know that. So let this supremum of n be n. That's what we have said. So n belongs to natural number implies that n plus 1 will also belong to natural number. We know what is natural number. So let's say 1. 1 belongs to natural number. We know that. Does 1 plus 1, that is 2, belong to natural number? It does. Okay, so let's say 2. 2 belongs to natural number. Does 2 plus 1 belong to natural number? It does. That's what they're trying to say. Now there is this n plus 1, which is less than equal to m. Why we say n plus 1 is less than equal to m? We say it because m is the upper bound of n. If it is upper bound of n, it obviously has to be upper bound of n plus 1, because n plus 1 belongs to set n, and all the elements which belong to set n are going to be less than their upper bound, which is m here. That's what we have written, and we have to write for all values of n belongs to natural number. We have to write this. What we did here is nothing but we shifted this plus 1 here. It became minus 1. That's it. For all values of n belongs to natural number. Therefore, m minus 1 is an upper bound of n. See, what happened here is m minus, we saw that 1 plus 1 shifted here, it become minus 1. So m minus 1 becomes greater than n, which means that this element right here, so let us say m was 5, okay, and m minus 1 will become 4, right? So 4 is greater than this element n, which we had considered as 1. So if this element is greater than this element which belongs to natural number, this becomes an upper bound, right? First it was this, because this m was greater than all the elements of the natural number, right? That's what we have proved above. Now m minus 1 is greater than n, and n belongs to natural number. That's what we have been writing. N belongs to natural number. Therefore m minus 1 becomes the upper bound of the set n. That's what we have written. M minus 1 is an upper bound of n. Okay, so we know that m is the supremum of natural number here, and m minus 1 is the upper bound of n. Now a very simple question I want to ask you is, upper bound and least upper bound, which one is the greater? Okay, is upper bound bigger or least upper bound bigger? We all know that upper bound is bigger. Why least upper bound is smaller? Because it is least of all the upper bounds. Okay, this element right here is the least of all the upper bounds. So other upper bounds are going to be greater than this least one. Here we have m, right? What is this? We saw that it is the supremum of n, which means it's going to lie here. That is the least upper bound. What is m minus 1? M minus 1 is nothing but it is smaller than m, right? M minus 1 is going to be smaller than m, which means it cannot lie here. So we don't know what is here, but we can't say that m minus 1 will also lie here and m will also lie here. It is not possible, right? Because m is the least upper bound. And where did this m minus 1 come from? Because m minus 1 is less than m, right? And least upper, but this is the least upper bound. So any other bound cannot be less than the least upper bound. That's what we know, right? And which is a contradiction, since m is the smallest upper bound of n. That's what the Archimedean principle is about. So then we write Therefore, there exists n naught which belongs to natural number such that x is less than n naught. Okay. This supposition of ours is wrong. Okay. This supposition, this is by contradiction. We this is what we supposed. N is less than equal to x, but it proved to be wrong because here we are getting a contradiction. Here we are getting something different, which is wrong. Okay, here we are getting something wrong. Therefore, this is a wrong condition to be solved. Therefore, there exists n naught, or we are not taking n because we have already took this element n in the above proof. Therefore, we do not take this n. We take this new element n naught which belongs to natural number such that x is less than n naught. And if we put it like that, we would not get this thing. Okay, that's why we say it to be like this. So this condition is valid. This condition which we proved right here is not valid. Okay, so why did we do this, you may ask. Now why can't we just take this condition and prove it right away? Now we can't take this condition because there is no such proof by taking this condition and then proving it. So what we do is we take the reverse of it, that is we take x is greater than n naught and we try to solve it, and we get some contradiction like this, and we say that no, that is wrong. Okay, if instead of directly proving it like this, we put it into a different form. Okay, basically we just shift the values and then we try to solve it, prove it. Okay, and we get this contradiction, which means this is how you write it. That's it. Thank you for watching. Bye.